Hello everybody and welcome back. My name is Artyom and in today's video we are going to understand what does big annotation mean and consider the time complexity. So let's get to it. So the agenda for today looks as follows. First of all, we're going to consider why you should know about big annotation as a software engineer and why it's helpful. Then I will explain the definition. Then we'll go through the types of big annotation from constant to factorial. We'll check considerations to not make mistakes. And in the end of the video, we'll make a self-check to review that you understood the topic correctly. So let's move on. Why it's essential to learn and master big annotation? First of all, it helps you to determine the most effective solution for tasks that you're trying to resolve. Secondly, it helps to optimize already implemented solutions. And the last but not least, most likely you will not pass the coding interview if you will not master this topic. Definition. Big annotation is a language and metric that describe the efficiency of algorithms. I took this definition from that book, Cracking the Coding Interview by Gayle, Laakmann, McDowell. And to be more precise, big annotation is a way to describe how long algorithm performs as its input size grows. And we'll see it visually on the next slide. Types of big annotation. I found this chart that shows all of the important time complexities that you should know, and it's nicely visualize them. So on the bottom axis we can see elements, and on the left hand side axis operations. We can see that O1, which is constant time, is the fastest one because it doesn't matter how many elements we have, it always will take the same amount of time. Then goes logarithmic, after that linear, after that linear arithmetic, n log n, then n square, which is quadratic, then 2 power n, which is exponential, and the last one is factorial. And we'll go through all of them one by one. Constant time complexity, as I mentioned, the main benefit is that it takes the same amount of time. For instance, on this function, which is sum, we have two parameters with a primitive type int. Due to this, it doesn't matter what values we'll receive. The parameters will do the same amount of operations, which is 1, just a sum. Doesn't matter what values we'll get. Let's consider linear time complexity. Now we have the same function sum, but it has in parameters array. It returns the sum of elements of the array. So basically, now we depend on the number of elements of the array. So in case we have array as here with the 5 elements, obviously we have to make 5 iterations through this cycle before returning the result. And if we would have array with let's say 10 elements, it will take 10 iterations or 10 operations in worst case scenario. Hope that makes sense. The next complexity that we're going to consider is quadratic or n square. So in this example we have square matrix, we call it A, and it has 5 rows and 5 columns and one single method which is in 2D, and complexity of this method will be n square. Why? Because we have here the nested loop, and when we have nested loop we do multiplication. So to print all of these elements takes 25 iterations. So number of rows that we have is 5, number of columns that we have is 5. Due to this is 25. Otherwise we can say that it's 5 power 2, which is 25. The same thing. So hope that makes sense. So the next is logarithmic complexity, and to understand logarithmic complexity, need to know what does logarithm mean. So we can understand it by the following formulas, where is logarithm, b is base, and n is the argument, and x is exponent. This can be calculated or transferred to the mathematical way as follows. So p power x equal n. And let's make some simple example. Let's say logarithm base 2 argument 8 equal x, and we need to find out what is the value of x. We can find out it by the following way. 2, which is base, and x equal to 8, and we know that 2 power 3 is 8. So basically x equal 3. And in big O notation, we always take 2 as a base. So applying the formulas that we just learned, we can say that if you want to, for instance, implement some binary search, which is time complexity is log n, in sorted array with 8 elements, it will be required to make 3 iterations, because logarithm 8, as we know, always we have base 2 when we talk about time complexity in terms of big connotation, because 2 power 3 is equal 8 due to the formulas that I showed you. So it will take eventually 3 iterations in worst case scenario to find some element in the array by binary search. Let's consider a practical example of log n time complexity. So what we have? We have here the array, which is called search field, which has 8 elements, and we have method for searching, which is called binary search, and we're gonna find number 56 in this array. And on this line, we're gonna print the number of steps that we made and the position of the element, which is 7. Cool. And let's go step by step and understand how this function works. So in the beginning, we're trying to find the middle element. How we're gonna do this? We divide the length by 2. As far as length is equal 8, we divide it by 2, we're getting 4 in the output. Going to the next step, switch and several cases. As far as number with index 4 is 16, 16 is lower than 56. We're gonna go to this case. And here we make recursion. What happens? We do slice and receiving only these elements, because middle plus 1, it's 23, and until the end, until 56. So on the first iteration, we've got this array. On the next iteration, we divide only this array to 2 and getting 1.5. As far as it's integer, we remove floating part, which is 5, and receiving just 1. One index has 38 in this slice. And we're getting 38, and going through this loop again, it's lower than number that we're trying to search, 56. We go again here. And once again, we iterate to one step further, which is 56, and the rest of the part. And we don't have any elements further. So we take only 56, and as far as we took only 56, it doesn't go to any of these cases, it goes to default, because the median equal to search. And yeah, we just return the result. That's it. And it took us only 3 iterations. And as we know, logarithm 8 equal 3. Yeah, because base is 2. 2 power 3 is 8. So we found our element. And let's run this code to find out that we are correct and this actually works. Go run main.go. Yeah, and we can see that position of the element, which is 56, is 7, and we made just 3 steps to find this element. So this is basically it. The next is n log n time complexity. It's usually used in sorting algorithms such as quick sort, merge sort, selection sort, and so on. And in this video, we are going to consider merge sort algorithm. Let's take a look into mental model of implementation of merge sort. I found this example on the Wikipedia, and it helps you to understand the big picture of how merge sort algorithm works. So as you can see here, we have unsorted array of 7 elements, and we execute merge sort function. What it does under the hood, it divides array into halves, and we execute the same function recursively, which is merge sort. And we split this array into halves. Here we do the same things, and we end up to having small arrays which have only one element, and we move to the merge stage, which mark as green here, where we merge the small arrays into bigger one and in sorted order. So as you can see, 27 goes in the beginning because it's smaller than 38. Here the same thing, 3 in the beginning, then 43. Then when we have bigger array, we just repeat the same thing. We just merge our arrays in sorted order, and in the end we having fully sorted array. So hope that makes sense. From practical point of view, algorithm looks as follows. We have main function where we execute merge sort function, and merge sort function has merge function, which is helper function, which is responsible for merging these small arrays in sorted order, and merge sort splitting arrays. And we can see here if statement, which helps us to find out when we have arrays just with one element. In that case, we just return these items. And afterwards, if we still have some elements like this one, still have such arrays where we have several elements, not only a single one, we recursively execute merge sort and split array into halves. This part takes log n, logarithmic time complexity, because with each iteration we have less and less elements in our arrays. And merge sort function, it takes linear time complexity, because here we have sequence of loops. We don't have nested loops here, so we can count them as a 3n in terms of time complexity, but we remove constants. So due to this, we're getting n. Yeah, so this is my explanation of how merge sort algorithm works and why it takes n log n time complexity. We have already captured most of the popular time complexities, and now the time to consider exponential and factorial. A good example of exponential time complexity is recursive Fibonacci function. And in this example, I as well created a counter variable, which helps us to find out how many operations it will take to find the result of Fibonacci recursion. So let's say we're going to add 4 as the parameter. And we'll know that it will take 9 operations to get a result. But if we'll add here, for instance, 8, the number increased exponentially. Now it takes 67 iterations. And if we'll update it to 20, let's say, then the number of iterations grow significantly. This is an example of exponential time complexity. We use factorial time complexity when we are computing all possible permutations of a given input. As far as probability that you will face with such time complexity is really low, we will not go into details, and I just listed on this slide popular problems. So first one is to find all permutations, and the second one is traveling salesman via brute force search. Now let's take a look into considerations which we need to take into account to not make a mistake when we will try to compute time complexity. The first consideration stands for when we don't have something which is nested in the loop, we summarize the complexity. So for instance, in this example, I have print summed function which prints multiplication and sum of the elements of the array. And here we can see one loop and another, and they're not nested. So due to this, we summarize the complexity. And basically this is first consideration. The second consideration, when we calculate big O time complexity, we usually remove the constants. So due to this, n plus n equal to 2n. And if we'll remove constant, we'll get just On. So this function has linear time complexity. The next consideration that we mostly already captured stands for when we have something which is nested to the loop, then we do multiplication. So in this example, with quadratic time complexity, we have for loop and nested for loop, which goes through the rows. So due to this, we do multiplication of rows to values. And it's the same as n multiply n, and it's equal n squared. So that's it. The next consideration stands for complexity of each input is calculated separately if they don't have the same length. So on this example, a bit updated print summed function, and we have two parameters now. And as you can see, parameter b is a bit bigger, has bigger number of elements. So due to this, they calculated separately. And as a result, we get m plus n. The last consideration stands for drop less significant terms. What does it mean? It means that as far as we have two parameters here, m, and we calculate m plus n, m array or slice in terms of Go, it's lower than array 2. Due to this, we can drop it and we'll have just On as a result. So it still has linear time complexity. Now is the time to check what you have learned so far. The first task. Let's try to guess complexity of the following function. This task is quite tricky. What this function does, it makes sum of all of the elements of the binary tree and returns the result. So pause the video and prepare your answer. Hope you prepared your answer. The answer is it's a linear time complexity. Why? Because to sum all of the values of the binary tree, we have to go through all of them. So we depend on the number of the elements on binary tree. The next task. What we have? We have two arrays and function with unordered pairs. And you need to guess the time complexity of this function. So pause the video and prepare your answer. Hope you prepared your answer. The answer is A multiply B. Why? Because A and B have the different lengths. So due to this, we calculate them separately. It will not be quadratical time complexity. So I hope it was kind of cool. I hope you enjoyed. If you did, like this video, hit the subscribe button, and I will see you in the next one. Bye bye.